So, we will begin our study of algebraic structures with an introduction to the algebraic structure known as groups. We will understand this by solving, we will introduce the notion of groups by solving a puzzle. I will first describe a game that many of you may be familiar with. So, this is known as the peg solitaire game. So, this game is a single player game and it is played on a board which looks like this. So, you can imagine these holes as places where a marble can be placed. Okay. So, the initial configuration, all the positions will contain marble. So, let us say that the darkened positions are devoid of marbles. Okay. So, if I mark it in black, that means there is no marble at that particular position. Okay. And so, this is the starting configuration. There are marbles at all the positions except at the very center of the board, and there are certain moves that is available, and you can perform these moves on the board, and the final configuration is given. The question is whether you can reach that particular configuration. So, we need to describe what the moves are. So, center position is the only. So, the standard starting configuration is one where the center position is devoid of any marbles. So, let us look what is a generalized move like. So, let us say there are two positions which are filled with marble and there is a vacant position next to it. So, that these positions are one after another, they are adjacent position. They can either be in the horizontal position. So, this is the horizontal case, or you can have an arrangement where there is a vertical alignment of three positions such that two of them are filled with marbles and the third one is empty. So, this is the vertical case. Okay. So, in this case what you can do is you can allow, so the move is described as the leftmost marble can jump to the vacant position, and if you jump over a marble, the middle one is removed. So, from this configuration we will end up at the following configuration wherein you have two empty positions and one position filled with a marble. So, basically if you name this as A, B and C, where A, B are occupied position and C is an unoccupied position, then the marble from position A can be transferred to the position C which is empty, and in the process you can remove off the marble that is there at position B. In case of vertical alignment also you can do the same thing. So, if you name these positions as alpha, beta and gamma, the marble at gamma can jump over the marble at beta to the position alpha, and in the process the marble at beta position is removed. Now, there are other moves as well. For example, here the move is from left to right, you can have it from right to left, top to bottom, all those are fine. So, basically any move is of the following kind: you need to find three positions on the board which are next to each other. They should be consecutive positions such that the extreme positions, that is not, if you find these three consecutive positions either horizontal or vertical, the middle position should surely contain a marble and one of the sides should be empty. In that case you can transfer the marble to the empty position and remove the other two marbles. So, that is the move. Okay. Now, the question is, if you start with a particular configuration, can you reach other configuration? Note that any move, horizontal or vertical, will reduce the number of marbles on the board. So, in this starting configuration there are along the arms there are 6, so 6 into 4 plus 9 positions, out of which 1 is empty. So, into 8 marbles are present, that is 32 marbles are there on the table. So, 32 marbles to start with. And then the question is, can you reach a configuration with exactly 1 marble? Okay. So, you can try this out, and maybe after it is slightly difficult, but you can figure out that there are you can reach a configuration where there is only 1 marble remaining. So, let me just describe some configurations from which there are no moves. For example, so if you had marbles at the alternate positions, let us say marbles in the chessboard pattern, so suppose after moving some number of marbles around, you reach this particular configuration. Here you can see that there is no further moves possible. Okay. So, if you call this as first position and this is position number 2, in position number 1 there are many moves. For example, you can consider these 3 positions and make a move, or you can consider these 3 and consider a move, or you can consider these 3, or you can consider these 3. So, many moves are there, and after the first move is made, there are again many moves that are left. So, you could choose any of those things and keep on repeatedly doing. Suppose we reach the configuration 2, then from there are no further moves possible and there are no undos. So, that will be a position in which you get stuck. Okay. Also, if you have just 1 marble, there is no way you can move anything around. So, that is also a dead end. So, question is, starting from 1, can you reach a position, a configuration with precisely 1 marble? Okay. The answer to this question is yes, you can do that, but what we will consider in this lecture is it's a variant of this, in the sense, can we reach a configuration where there is only 1 marble, but that is at, let us say, this corner position. Okay. So, the only marble remaining is appearing at one of the corners. Is this possible? Okay. And to this question, if we want to list out all the possible moves, the first move itself there are 4 possible moves. Okay, and in between there could be multiple number of moves. So, it could be a very large number of moves to explore if you wanted to conclude that it is impossible to reach a particular configuration. You can model it as a search through the configuration space. So, each configuration can be described by let us say a bit vector with 33 positions. Each a bit vector of length 33 tells whether a marble is present at a position or not, and from each bit vector you can move to certain other bit vectors. You can move from one position to another if there is a valid move which will take you from one to other, and then this can be reformulated as a search problem on a graph, but the search space is really huge here. So, we can't really hope to do a computerized check to figure out whether certain configurations are reachable or not. And if the same configurations, if it is imagined on the same game, if it is imagined on a larger board with more positions, then it is hopelessly intractable. But we will see that in some cases we can use some clever arguments to say that you cannot reach certain configurations. Okay. So, we will use some standard tools from computer science while we argue about these. The moves are non-deterministic. In the sense, we have no control over the choices made by some player while he is playing this particular game. So, in order to argue that none of the sequences of moves can reach a certain configuration, we need to answer about all possible moves. Okay. The tools that we will use to solve this, the main thing is this is a key thing that is used in many proofs. This is called as invariance. So, here we have some particular, so we think of this as an algorithm. So, some adversary is performing some sequence of operations on some configuration space, and each configuration has to follow certain rules. It is either the horizontal case or the vertical case, but we will identify some quantity associated with each configuration such that that quantity remains invariant, it does not change even after the moves is made. Okay. And once we have established an invariant, what we can argue is that no matter what are the moves done by the adversary, the first configuration and the last configuration, whatever are the sequence of steps that take you to the last final configuration, the invariant must be satisfied. And if we can argue that the configuration that we want to end up with does not have the invariant property, then we can say that look, that is a configuration that is unreachable. Okay. So, let us identify what is the invariant property here. So, in order to describe the invariance, what we will need is the idea of groups. We will not initially formulate it in terms of group theory, but we will explain it via simpler methods. So, so what we are going to do is the following. So, look at these positions. We are going to number these positions in a certain way, and based on the numbers that we give to these positions and the presence or absence of marbles on individual position, based on that we will come up with a numerical quantity. Okay. So, there are 33 positions on the board. So, what we will do is we will look at this board configuration, and to each position in the board we will give a certain color. Okay. So, these colors, let us call the colors as A, B and C. So, this position gets color A, and the next one gets B, and the next one gets C, and we do this systematically. So, A, B, C. So, this is again going to be A, so A, B, C, A, B, C, A, B, C. This is also going to be an A, it's going to be a B, and these positions are going to be the C positions. Okay. So, we looked at the board position and we gave colors, or we labeled each of these positions as A, B and C. Okay. Now, we are in position to determine the value of the board. So, the value of the board is determined by combining the colors given to the positions which have marbles in them. Okay. So, let us say the positions which do not have marble, we can probably cross it out. Okay. So, initially this position did not have a marble, okay, and all the other positions contain marble. So, at any position the value of the board is obtained by combining the values of the positions. I mean, the value of the board is determined by combining the colors at the positions where there are marbles. Okay. So, initially there are 32 such positions, they are combined and we get a value. Okay. Now, how are these colors combined? Okay. So, we will follow the simple rule that whenever two distinct colors combine, you get the third color. Okay. So, if a red and a green combine, you will get a blue. If a blue and a red combine, you will get a green, and so on. So, two distinct colors when they combine, you get the third color. And if a color combines with itself, you will get a brand new color. So, there is a fourth color in the picture, let us denote it by pink. So, this is the fourth color. Okay. So, let us just write our setup. So, we define what is the value of a board. This is obtained by combining the colors at the occupied position. Okay. So, we have defined the value of a board by combining the colors at the occupied position. Okay. So, given any board, we know how to compute the value. Now, this combination means the following. If you think of C1 and C2 as the color, and if C1 not equal to C2, then they combine to produce C3, and if the colors are same, if C1 is equal to C2, then they give rise to C4. So, C4 is a new color. Now, this combination, rule 1, when you think about it, this applies only to colors red, green and blue. If it was the fourth color, okay, if it was the pink color, okay, when that color combines with any color, it does not change anything. Okay. So, that is the third rule. C4 does not change any color. In the sense, if you combine a red and a pink, what you will get is a red. If you combine a green and a pink, you will get a pink. If you combine a blue and a pink, even then you will get a pink color, and pink when they combine, you will still get a pink color. Okay. So, we have described the rules of combining colors. There are 3 colors on the board, but when you determine the value, we had introduced a fourth color. So, 2 colors combine and give rise to the color which is not present if these 2 colors are red, green and blue. The fourth color was used at any time, that will not change the color of anything that it combines with. Okay. So, now we have defined formally what is the value of a board. Now, let us look at the initial value of the board. Okay. So, the way in which these colors combine does not really matter, because all that matters is if you have, let us say, so you can convince yourselves that the order of combinations do not really matter. Okay. That means whether a red first combines with the blue and then combines with the green, or the other way, really does not matter, because, so let us say we write down these colors C1. So, if you arrange them as alpha 1, alpha 2, alpha k, these are the colors Now at any point alpha 1 alpha 2 is same as, if you combine alpha 1 and alpha 2, that is the same as combining alpha 2 and alpha 1. So any rearrangement of colors is still okay. So any order of combining them will give rise to the same color. Okay. So for this board, what is the initial value of the board? Okay. Think about it for a few seconds. So we can determine it by looking at the rows, looking at this diagram carefully. So if you look at the topmost row, the red and green combines to give a blue, blue and blue combines to give a pink. So any three of them, because all these were occupied positions, all these give rise to pink. Okay. And the pinks, when they combine with each other, they do not do anything, they do not bring in any change. So you are going to get a pink by combining these. Okay. And the red and blue were occupied position, whereas the green in the center was unoccupied. So the total product is going to be just the product of, or the total value of the board is going to be the value that you get when you combine a red with a blue, and that is going to be a pink, and the others combine and give a pink, pink and pink combines to give you a pink. So the initial value is going to be pink. Now here is a crucial observation, which is where we use the invariant property. Moves do not affect the value of the board. Okay. So look at the value of a board before and after a move is performed, the value remains the same. Why is this so? Because let us look at any move, think of it as horizontal, vertical is similar. So you have three positions. So let us say we denote them by alpha 1, alpha 2 and alpha 3. Okay. Two of them are going to be occupied. Let us say the occupied position is what we call as alpha 1 and alpha 2, and alpha 3 is the unoccupied position. So this was the unoccupied position, and this will change to 2 unoccupied position and 1 occupied position. The initial value of the board is going to be obtained by looking at all the other positions. Okay. So let us say this is the initial board, or let us say before move configuration. Okay. So let us say A denote the remaining of the board, and then there are these positions alpha 1 and alpha 2. Okay. The occupied positions inside this, they will combine, and let us say it will give some value A. When alpha 1 and alpha 2 combine, what you will get is clearly alpha 3. So the initial value is A combined with alpha 3. So I will write it as A followed by alpha 3. Okay. So this is the initial value, and after the move these two positions are unoccupied, whereas the other positions remain unchanged, and alpha 3, which was an initially unoccupied position, now becomes an occupied position. So the value after the move is going to be again A, because those were the other positions, the positions other than alpha 1 and alpha 2 and alpha 3, their value if you denote it by A, that followed by the only occupied position, that is alpha 3. So if you combine these, whatever value you get, that is going to be the value of the board. So you look at any individual move, that does not change the value of the board, and we argued that at the start the value is B. Okay. So after any move, no matter what move you perform, in what order you perform, the value of the board should still remain B or green. Okay. So if you call this as green position, the value of the final board should be green. Okay. So now if we ask whether we can obtain a board position with precisely one marble at this position, we can say that that is not possible, because that would be a board position whose value is red, but the only allowable board positions are the ones in which the value is green. So, this was a neat little puzzle wherein we solved by identifying a crucial invariant property. What has this got to do with group theory? Okay. So, here we talked about objects combining in a certain way. It is a rather arbitrary way of combining objects. We found combining method very useful to solve our problem, but many different objects, I mean, can be studied by this kind of methodologies, wherein we identify some structure in the problem and use that to solve certain problems. Okay. So, what we have in any algebraic structure, so let us say what is an algebraic structure. So, an algebraic structure is a set. In our case, this was colors and some operations on it. And that was the way of combining. Okay. So, depending upon what are the properties that you insist of the operation, you will get various algebraic structure. Okay. So, in our case we had a set of colors, 4 colors, and we told how 2 of them can combine to give rise to a third color. So, the particular thing that we used can also be called as a group. So, let us understand what are groups. Okay. So, formally we need to understand what are binary operations, because this combining we are restricting to combining 2 at a time. You can combine more at a time, you will get more complex objects, but we will restrict ourselves to binary operations. So, let us understand what are binary operations. So, you have a set, let us call set as G, okay, and a binary operation. So, we could use any symbol, let us say plus, multiplication, subtraction, all these are examples of binary operation. So, that would be thought of as a function from G cross G, okay, to G. That means take 2 elements and map it to a third element of the set. Okay. So, it can be thought of as a function which takes a pair of objects from a set and gives rise to an element of the set. In the functional form, this can be written as star followed by x, y. It means it is combining x and y, and it is a function with 2 parameters x and y. But when we look at algebraic structures, the most common notation for writing star x y is x star y. We will write it in between and not use the functional notation. Okay. So, the usual binary operations you can think of plus, defined on either as a set of natural numbers or the set of integers or on the set of real numbers or complex numbers and so on. Okay. So, that is a binary operation. It takes 2 elements, combines them and gives a third element in the same set. Now, if you think of the subtraction operation on the set of natural numbers, that is not well defined. So, we should not really talk about subtraction on natural numbers, because if you subtract 3 and 8, if you look at 3 minus 8, the result is not really natural numbers. So, we want, when we say binary operations, by definition they take 2 elements and return a third element. So, 3 minus 8, the answer is minus 5, and that is not an element of n. So, minus cannot be viewed as a binary operation on this particular set, but of course, it can be viewed as a valid binary operation on the set of integers. So, in order to define what are groups, we will need another property known as associativity. Okay. So, if you have, let us say, elements A, B and C belonging to G, we could first combine A and B and then combine it with C. or we could have first combined B and C, and A is combined with the result of that. If these are both equal, then we say that the operation is associative. Okay. So, formally for every A, B, C belonging to G, if A star B star C is equal to A star B star C, use parenthesis to indicate which of the operations is done first. If this is equal, then we say that star is associative. So, note that in our color combination example, the operation was indeed associative. If you had first combined, let us say if A, B, C were 3 colors, some of them may be equal or unequal, each of them could be one of the 4 colors. So, if you you can verify that A star B star C is equal to A star B star C. Okay. So, that was indeed an associative operation. In fact, it had an additional property, whether you, we were just bothering about combining 2 colors. Which one is written as the first color and which one is written as the second color does not really matter. So, that is called as commutativity property. Okay. So, A star B is same as B star A. So, when we looked at the binary operation, that was taking 2 parameters, and when you talk about 2 parameters, what is the first parameter and what is the second parameter is important, but if it is commutative, then the order does not really matter. A star B is equal to B star A. By our definition of combining colors, we did not really think of it in the functional way, because this operation we wanted it to be commutative. Okay. So, now after we have understood what is binary operations, what is associativity and what is commutative, we can define what is a group. Okay. Okay. So, the formal definition, a group is a set G with an operation star. Okay. We call it a star, you can use any other symbol. So, it is a pair, the first is a set and the second is an operation such that this is 4 properties. First, star is a binary operation. Okay. So, some books might say that this operation star is there is closure, but that is when you say binary operation, it is taken care of. Okay. So, this is a binary operation and you want this to be associative. Okay. That means for any 3 elements from G, A, B and C, A star B star C, no matter how you parenthesize it, you will get the same result. And the third property is existence of identity. That means there exists an element, let us call that as E, such that for all A belonging to G, A star E is equal to E star A, and that is equal to A. Okay. So, there is a special element, we will later on prove that there can be only one such, if it is a group, then there cannot be 2 such elements. So, here when we say the definition, we say that there is an element, the property of identity says that there exists a special element such that any element of the group when multiplied with that element will give rise to the same element, it does not change things. And the fourth property is that of inverse. So, formally this means for every element A belonging to G, there exists an element B such that AB A multiplied by B or A star B is equal to B star A, and that will be equal to identity. So, if you can find a set equipped with a binary operation, which has these properties, that is, it is associative, it has an identity, and every element has an inverse, then we say that this is a group. Okay, so let us look at our example. We had 4 colors. Let us call these colors as by letters. So, this was our special color which will do the role of E or the identity, and let us call this as A, B and C, and you can check that for any 3 elements. So, let us say x, y, z. So, x star y star z is equal to x star y star z. Okay. If x is identity, so we have to verify for all cases. If x is identity, then what we have here is y star z, that is because E combines with anything to leave it unchanged. Okay. So, if x is E, then this is going to be, the left hand side is going to be y star z, and the right hand side x combined with y is going to be y, and the entire product is going to be, or the entire expression of the on the right hand side is going to be y star z. So, when x is equal to E, this is clear. When any one of y and z, if any of them is E, then the same reasoning works out. So, we may assume that they are all different from E. Okay. And if 2 of them are the same, so one case is when all 3 of them are the same. If all 3 of them are the same, then does not really matter, because left hand side and right hand side, they all give rise to. So, let us say x star x, okay, x star x is going to give you E, and x star E is going to be x, and the other side is also going to be the same thing. Okay. So, when all of them are the same, does not matter. If all of them are distinct, then x, y and z, when they are all distinct, y, z will combine to give x, and the entire product is going to be E, and the right hand side is similar, x star y is going to be z, and z star z is going to be E. So, when all of them are same, all of them are different, those cases are taken care of. So, the only remaining case is when 2 of them are the same. So, if y equals z, then y star z will give you E, and x star E is going to be x. If y is equal to z, then the left hand side is going to be x, whereas the right hand side, x into y will be the third missing element, which we will call by w, and w multiplied by z will give you the missing element here, which is nothing but x. Okay. So, in that case also things are going to be the same. So, here we assume that y and z are equal. If x and y are same, then the same reasoning applies, and so on. Okay. So, we can verify in a systematic manner that the operation is associative, and the pink color or E automatically serves as the identity, and every element has an inverse, namely the element itself is the inverse. I mean, you take any element, its inverse is itself, because you multiply it with itself, you will always get identity, okay, or you combine it with itself, you get identity. Okay. So, in our example, in case of the in solitaire problem, we had basically assigned an element of a group to each position in the board, and the value of the board was the product of the occupied positions. Okay. So, let us look at some properties of groups. The first property that we will state is that the identity is unique. Every group will have a unique identity. look at the definition, we just said that there exists an element, there could be multiple. Okay. How do we rule out that case? So, suppose E1 and E2 were both identities of a group. We want to show that E1 is equal to E2. So, we just need to look at E1 star E2. Because E1 is the identity, this has to be equal to identity multiplied by any other element should leave that other element unchanged. So, this should be equal to E2. Also, because E2 is an identity, we can say that E1 combined with E2 should leave E1 unchanged. So, this should be equal to E1, and therefore, E1 is equal to E2. So, there is a unique identity. The next property is that the inverses are also unique. Okay. So, the inverse, we will denote it, we will have a notation. So, if you have an element x, since its inverse is unique, there is a specific element, we will, once we have this particular fact proven, we can denote it by x inverse. That will be the unique inverse of any element x. Okay. How do we prove that? Suppose, let us say A and B are both inverses . Okay. So, what do we know? Because of this, we can say that XA is equal to identity, AX is equal to identity, XB is identity, and Bx is also equal to identity. Okay. From these, somehow we need to argue that A and B are same. Okay. So, let us look at this equation, XA is equal to identity. Now, if we multiply with B on the left, what we will get is B times XA or B star XA. So, when I write XA, it means I am just swallowing up the star. Instead of writing star each time, I will just write the letter. So, when I write BXA, it means B star X star A, and associativity guarantees that the order really does not matter. Okay. So, BXA, that should be equal to B times E, and that is B. But here BXA we can write it as B times X times A. Okay. And since Bx is identity, this is equal to identity times A, and that is equal to A. So, we get A is equal to B. Okay. So, every element X will have a unique inverse. In particular, you can, if you look at the element A, the identity element, its inverse has to be itself. Okay. Because it satisfies the property that, so E times E is equal to E, therefore, E is an inverse of E, and since it is the there is only one inverse, E has to be its own unique inverse. And another property of inverses is, if you look at X inverse, that is some particular element, its inverse is equal to X. That is straightforward, because by definition of inverse, X times X inverse is equal to X inverse times X is equal to identity. Okay. Now, if you let X inverse play the role of X, then this equation says that the inverse of X inverse is equal to X, because if you denote this by, let us say, alpha, if you denote X inverse by alpha, alpha times X is equal to X times alpha, and that is equal to identity. Therefore, the inverse of alpha must be X. The third property of inverses is, if you multiply two elements A and B and take their inverse, that is going to be equal to the product of the inverses, but done in the inverted fashion. So, this will not be equal to A inverse times B inverse unless the group is commutative, but in any case it will be equal to B inverse times A inverse. Okay. That is because if you look at the product B inverse A inverse times AB, okay, this will be equal to identity, and this will also be equal to AB times B inverse A inverse. Okay. So, this has been bracketed in a certain way, but because of associativity properties we can just bracket in other ways and you can combine them and see that they will give identity. Okay. So, we just need to look at B inverse times A times B. Okay. So, the initial combination of A inverse and A will give you identity, B inverse times identity will give you B inverse, that multiplied by B gives identity. The same thing applied on the other side will again give you identity. So, A B inverse is B inverse times A inverse. Okay. So, we will stop here and we will continue our exploration of algebraic structures in the coming class.